everyone. Welcome to EDA Day. I just want to do a quick poll of the audience. So, do we have any Taylor Swift fans in the house? Ah, a couple of brave people. Okay, a couple of people. All right. What about maybe something a bit more popular? In the last 20 years, has anybody in the room tried to go to or been to Glastonbury? Okay, a couple more hands, but like tiny amount of hands. What about any opera fans in the house? Anybody into Neville Holt? Maybe Neville Holt opera? No? Okay, definitely Google it. Beautiful if you're looking for something to go to. Black tie, all very scenic, opera outside. But what do all these things have in common? And I'm not just trying to understand what your music taste is, although, of course, I think that's a wonderful thing for us all to connect over. But these are all real-life events, if you like, that generate events and traffic on IT systems. All of these three events will generate a certain amount of hype, of buzz, and of pressure on our IT systems that support, in part, ticket sales for these events. Now, for those of you who aren't opera fans, I can assure you Neville Holt is very coveted. The members always get the best tables first because they also offer a lovely dinner service. So do definitely look that up. But I'm not telling you all of this because I myself am a Taylor Swift fan. I'm really not. There is some parts of this presentation that are about Taylor Swift. I'm much more of a disco girl myself. But I'm telling you this because I'm a fan of using event-driven principles for us to start changing our mental models on how we scale our IT systems. A lot of our mental models today are based on scaling IT systems based on load. So an infrastructure characteristic, if you like, of our IT systems. And it's really got nothing to do with our end users. So we're scaling our ticket systems, for example, not based on the number of opera fans that are going to be out there trying to buy tickets to Neville Holt, or the number of Glastonbury fans or Taylor Swift fans. When we're scaling, often we're looking at our infrastructure as that marker to tell us to scale. And today, what I'd like to talk to you about is specifically these sorts of events and how we can start adjusting how we approach scaling for them. My name is Natasha. I'm a container specialist at AWS. So this talk is going to be focused on containers. It is going to mention Kubernetes. So if that is of interest to you, you are certainly in the right place. As I mentioned, I am going to talk a little bit about Taylor Swift, but don't worry, it won't be all about Taylor. We're going to talk a little bit about scaling with Kubernetes, event-driven scaling with Kubernetes, and how we can help our Kubernetes scalers using a new system called Karpenter, and then some takeaways. So let's start with Taylor then. So the Eras Tour, if you haven't heard of it, you've probably been living under a rock. It's huge, quite literally record-breaking music event and tour that's happened. And it's the highest grossing tour of all time. So currently, I think it's standing at just over $1 billion. Experts estimate this could get to nearly $2 billion for this tour. Now, to put that in perspective, if there are any Elton John fans in the house, so we are really moving through the music genres today, this has grossed more than Elton John's farewell tour, which was also extremely difficult to get tickets for. But it's been huge. So it shattered attendance records all over the world. Also resulted in a 40% increase in the sale of friendship bracelets. So there was a song called You're Your Own Kid, which talked about giving friendship bracelets to your mates. So apparently that spiked 40% increase there in friendship bracelets. It's the highest grossing concert film of all time. So as well as the people that bought tickets to see Taylor Swift, around $250 million was generated from people buying tickets to see the movie of the concert. The US Travel Association estimated that it added around 10 billion to the economy as well through things like people purchasing travel, hotels, and food when they went to concerts. So a real injection there to the economy. And the seismic activity from Taylor Swift fans dancing around and bouncing quite literally created an earthquake. So that actually measured on the Richter scale. So it's huge. So for many, many fans across the world of Taylor Swift, this was sort of the greatest thing that's ever happened to her, to them rather. And this has also touched many, many other areas. But for some Taylor Swift fans, it wasn't such a great story. They didn't have such a great event. And let's start with sort of setting the scene for the Eras tour. So 3.5 million fans registered for pre-sale. Now, our ticket merchants that were supporting this pre-sale thought, okay, 3.5 million, that's an awful lot, given that we actually don't have that many tickets. So what we're going to do is we're going to divide these fans into 2 buckets. So bucket 1, 1.5 million fans who would be granted pre-sale access. And then we had another 2 million fans who would get access to pre-sale at some point in the future, some sort of pre-sale event. So already from an IT planning perspective and our IT systems that are going to support the process of actually buying a ticket, we've done some pre-planning, and we feel pretty confident that we're going to have 1.5 million fans who are going to be hitting our pre-sale systems and trying to purchase a ticket on pre-sale day. And these numbers that I'm about to talk to on this particular slide can all be found in an article on Sky News, which I've referenced at the bottom of the article if you want to read a little bit more. Unfortunately, this was not the story for many, many Taylor Swift fans. So for our ticket merchants that were supporting this pre-sale, they got around 3.5 billion system requests that actually hit their systems. So this is way, way more than they were expecting. So in terms of the ticket merchants that were supporting the pre-sale event, this was about 4 times the peak traffic that they'd ever seen on their ticket systems before. So a huge amount of load there on their IT systems. And this can be, really down to a number of different reasons. So one, our very keen pre-sale fans sharing their pre-sale access with their friends, having lots and lots of browsers open because they were so keen to get pre-sale. And also the ticket merchants believe that bots played a huge part in this as well. So 1.5 million fans turned into way, way more traffic than we were expecting. And Sky News actually estimate that if Taylor had wanted to fulfill all of the requests on that day, she would actually have to run her Eras tour 20 times in order to satisfy all that demand. So it was a huge, huge amount. So we went from having this quite safe event where we knew or had an idea anyway of how much traffic and load our IT systems would experience to something that was nearly unprecedented. So 4 times more than our peak traffic, and we've been able to handle. So you might ask yourself, could pre-scaling really have solved this? We knew when pre-sale was going to happen for the tickets. We knew how much traffic we were going to expect. We had some scaling mechanisms in place. Surely we should have been able to handle this. And there were a couple of reasons why we couldn't. So first off, the traffic estimates completely wrong. We didn't really account all the Swifties sharing the link with one another. We didn't account for the bots. We didn't account for all that additional traffic that we would get, and certainly didn't account for 4 times more than our peak traffic than we were expecting. Some of the systems that make up that end-to-end journey of purchasing a ticket aren't these lovely, loosely coupled modules that can be scaled and tinkered and changed. Sometimes we do have tightly coupled components that make up that journey. Perhaps we have applications that have an inbuilt queue. They haven't sort of externalized that queue. And that means they have a high blast radius if that particular application has a problem. As I mentioned, today we do see traditional scaling mechanisms rely on things like utilization. So we'll wait until an average utilization hits a particular threshold, and then we'll scale. But what we don't realize is that at that point, say, for example, we're scaling our IT systems at maybe 80% utilization. At 80%, we might already have some very sad, upset Taylor Swift fans that the ticket systems that they're interacting with are running slowly. So nothing about that 80% really tells us the experience that our Taylor Swift fans are having. They might already be unhappy. They might have already taken to X and whatever social platform Swifties use to vent their frustration at their experience so far. And also in that ticket purchasing journey, we have many dependent systems that we're interacting with. as a ticket merchant, or a ticket retailer rather, it's not only you that's part of that journey to actually purchase a ticket. So once your Swiftie has selected their ticket, added it to their basket, they then need to pay for this ticket. So that involves a whole other set of systems, which is something that I kind of want to step through and explore as a bit of a journey today. Because as a ticket retailer, maybe you pre-scale, maybe you know what traffic is about to hit you, but these other dependent systems may not. So if we think about a payment journey for our Taylor Swift fan there, because there were many fans who got to the point where they got their Taylor Swift ticket, they added it to their basket, they entered their credit card information, they're super happy, they've clicked pay, minutes pass, and then bang, they see a red text error code, don't know what it is, and they get bumped right back to the queue again. And they suddenly see you are user 182,461 in the queue. And then they've gone mad, they've turned to X, it's awful. But these dependent systems that actually make up this credit card journey maybe weren't expecting 3.5 billion system requests to hit them. So I want to step through that payment journey a little bit. So we've got our Swifties, we've got our ticket buyers, we've got the bank that they're using. So these people have a credit card, and when they make payments on their credit card, they're going to be interacting with a particular payment network. We also have our ticket merchant. You know, these are the people that have our tickets. And then we have what's called a merchant acquiring bank. And these are the institutions or entities that are authorized to take payments on behalf of like Visa, MasterCard, these sorts of entities. So these are all the players or the actors really in our journey to actually purchase our Taylor Swift ticket. And what will happen when we are stepping through this journey is that our ticket buyers are going to interact with our ticket merchant, and they're going to give their credit card information. Our ticket merchant is going to interact with our merchant acquiring bank so that they can grab, using whatever card scheme that our ticket buyer is using, to grab those funds. The merchant acquiring bank is going to communicate across our different payment networks, which will then communicate with the card issuing bank. And finally, that will send a message back to our merchant acquiring bank and then back to our ticket merchant to say whether this transaction is good and whether this person has sufficient funds in order to purchase this ticket. So it's this merchant acquiring bank that I really want to look at, because if we think about these dependent systems in our Taylor Swift payment journey, maybe our ticket merchant did some pre-scaling, because we had our pre-sale access, we had users signed up, we knew how many people were going to be hitting our ticket systems. But did the merchant acquiring bank? Now, this isn't based on an actual root cause analysis or post-mortem of what happened during the Taylor Swift ticket sale. This is just an example scenario, but I do urge you to go and read some of those post-mortems to learn a bit more about this. But if we double-click then on our merchant acquiring bank, so we have our actors in this journey, our Swifties, our ticket merchant, card issuer, the payment networks themselves, and then our merchant bank that's acting on behalf of, say, our Visas, our MasterCard to collect those payments. So our Swifties will make a payment for their Taylor Swift tickets. We've got here $100. If anybody is familiar, they were a lot more than $100, but that's something else for Taylor to talk about with her tour company. But we've authorized, we want to pay $100 for our tickets. So our ticket merchant then communicates with our acquiring bank and says, can you authorize this much money? And our acquiring bank has all of their payment systems, their clearing and settlement systems containerized, and they've deployed those onto Kubernetes. This is a Kubernetes talk, so that's where they're going to put those. So we're communicating with our acquiring bank and saying, hey, we want you to authorize this. And our acquiring bank has started to adopt event-driven architectures. So let's imagine they post an event to some sort of stream. In this case, maybe they're using some sort of broker or Kinesis, something similar. And then the acquiring bank will then communicate through the payment networks back with the card issuer to say, can you authorize this much money for this ticket? That payment's approved, that generates another event, and we then send a notification back to the ticket merchant to say, this amount's okay. At that point, our ticket merchant's like, okay, we know the money's good, let's tell the Swifties that they've got their tickets, and then the Taylor Swift fans rejoice, turn to X in happiness. And then behind the scenes, that payment is actually initiated from our merchant through their acquiring bank. That payment's captured, and then the clearing and settlement system will kick in to ensure that everybody knows that this payment has been made. This payment is taken then from our Swifties bank accounts. A bit is trimmed off the top as a fee from our acquiring bank, who have a fee for their particular services. But this is all driven through a series of messages and communications over the payment networks. And it's generating a series of events. So the events for, yes, the payment is approved, the payment's authorized, the payment has cleared in my system, the payment has cleared in your system, that payment is now settled. So this has all generated a series of events. And our acquiring bank has containerized all of their systems that can help support this process. And they've deployed them to Kubernetes. So now if we think about our Taylor Swift problem, we now want to ensure that we've scaled what we've deployed to Kubernetes. So if we think for a second then logically about Kubernetes and the different bits that make up Kubernetes. So first of all, we have our Kubernetes control plane. And if you are a user of Amazon EKS, which is our Elastic Kubernetes service, when you're using Amazon EKS in region, you get a managed Kubernetes control plane. And your Kubernetes control plane is made up of things like an API server, a scheduler, an etcd layer to manage the state of your Kubernetes cluster. If you're using something like Amazon EKS, all of this is going to be managed for you. But when you're thinking about scaling, you need to also think about scaling of your control plane if you are using something like COPS Kubernetes or a client cluster or something like that. You then have your data plane, and this is your compute that actually runs your workload. So for your containerized application, this is the layer that's going to provide compute to your workload. So really what we're talking about here is like your worker nodes, really, that make up your cluster. We then have cluster services, and these are, I suppose, applications, extensions, add-ons that you deploy onto your cluster that provide functionality to your workloads. So this is going to be things like core DNS or scalers, which is the case in this talk that I want to double-click on. And then we have your workloads themselves. So if you're the merchant, bank, these are going to be your payment, clearing, settlement systems that are containerized and deployed to your cluster. So we're going to explore the scaling of your workloads and then the scaling of the data plane to explore that today. So let's start then with the scaling of your workloads. So you've got these different payment systems that are going to handle all these payment transactions for all these Taylor Swift fans buying their tickets. And there are different mechanisms that you can leverage in Kubernetes to scale your applications. And all of those systems will essentially scale the configuration that's associated with the deployment that you've made to Kubernetes. So first of all, we have horizontal pod autoscaler. Now, this is all about how do we scale your application horizontally. So how can we add more instances of your application or replicas in Kubernetes terminology? How can we add more of those as your application is starting to experience load and knows it needs to scale? We then have vertical pod autoscaler, which isn't concerned with adding more instances or replicas of your application. It's actually concerned with how do we give more resource to your application? How do we give more CPU and memory? And then we have KEDA, which is our Kubernetes event-driven autoscaling. So both horizontal pod autoscaler and vertical pod autoscaler interact with the Kubernetes metric server, which means that they get access to the metrics that Kubernetes exposes to them. And in short, this really means CPU and memory. But we know that our credit card transaction is generating lots of events. So actually, we don't necessarily want to be scaling based on CPU and memory. We want to be scaling based on these events that are happening in our system. And KEDA is an approach that allows us to do that. And that's what we're going to be deep diving into today. But if you've scaled all your workloads, you still need somewhere for them to run. So this is your data plane. These are your worker nodes. And when you've got lots of instances of your application, you're also going to need to increase or consider increasing or decreasing the size of your data plane. And there are two approaches here that you could leverage to scale the data plane of your Kubernetes cluster. So the first is cluster autoscaler. And this is all about how do we add like or similar compute into your cluster to provide more compute to run those containerized workloads. We then have Karpenter, which I'm also going to be diving into a little bit today. This is what we like to consider to be application-centric scaling for your data plane. So cluster autoscaler will work based on a logical configuration that you've defined for your nodes in your cluster, whereas Karpenter will scale based on what your workloads actually need. And I will explain a little bit more about that shortly. So let's go back to application scaling then. So as we've said, this is all about scaling your containerized workload itself. So this is those payment systems, those settlement and clearing systems that are going to help us buy our tickets. How do we scale those? So HPA and VPA interact with the Kubernetes metric server. So they're using really CPU and memory to understand whether your application needs to scale or not. HPA will scale the number of replicas of your application. So once HPA kicks in, you might go from 1 replica to 2, or from 2 to 4, and it will scale the number of replicas horizontally. VPA works a little bit differently. As I mentioned, it's going to add more resource to your deployment. So it's going to increase the amount of CPU and memory that is provided to your particular deployment. It does this dynamically. You don't need to go and change a configuration to say, oh no, my application's suddenly resource constrained. Let me give it some more. The VPA system is going to do this for you. Now in the current version of Kubernetes, this involves Kubernetes restarting that pod. So that definitely is something for you to be aware of. There is a feature on the Kubernetes backlog so that this is done dynamically, so it will just happen magically in the background. Now, you might be thinking, why would I need to use VPA? Why wouldn't I just use horizontal pod autoscaling? I've got my nice kind of well-architected, loosely coupled, modularized payment system. Why would I need to use VPA? And we do see customers at AWS use VPA in a couple of different scenarios. So first off, we see customers using VPA when they are right at the beginning of their application journey, and they don't fully understand at that point as to what the CPU and memory requirements are for their workloads. So VPA is a great way to figure that out. So we do see lots of customers that use VPA in like sandbox or testing environments, run some load tests to get an idea of what their application needs. There are also many customers who are running containerized applications or pieces of software that they've purchased from vendors. So they are not the ones who are building that software that's going into that container. And that happens quite a lot when we think about financial transaction processing. Lots of the systems that are run by our financial services customers will be pieces of software that are purchased and then containerized. So often these are slightly monolithic in nature, which means that actually when you provide more resource to these applications, sometimes it does help them run, and scaling horizontally may not help your particular problem. So we do see different types of applications, and customers look at the different scalars. But vertical pod autoscaler is all about more resource. Horizontal pod autoscaler is all about more instances of your application. So where does KEDA fit in then? So both of those interact with the Kubernetes metric server. So they're both using CPU and memory really to scale. But we now know in our credit card transaction system that we're generating all these events, and we want to be event-driven. We don't want to scale based on just resource or just load. We want to be able to scale based on something more intelligent, perhaps something that tells us how much work our systems actually need to do. So how many people have clicked buy now in their ticket basket, for example. And KEDA allows us to do that. So it allows us to interact with a number of different event-driven or integration services to capture data and metrics, and we can use that to tell us when to scale. So rather than just using CPU and memory, we can look at the number of messages in a queue, for example, as a trigger to tell us when to scale. All of these colored boxes represent a different type of scaler that's available for KEDA. There are lots of AWS ones available. SQS is one that's there. If you were looking to build an event-driven architecture with AWS and you want to use SQS, there is an SQS scaler available, meaning you can look at the number of messages that are in a queue and figure out if you need to scale your system based on that. So when you deploy KEDA to Kubernetes, there are three key components, I suppose, that make that up. So we have our scaler. So this is our logical object, if you like, that will look at a particular event component. So this will be the thing that either looks at SQS or Kinesis or whatever event technology that you're using. We then have our metrics adapter, and that takes the metrics from the scaler and converts them into a form that Kubernetes can understand. You then have your controller, which then decides, based on those metrics, do we need to do something? Now, it's important to note that KEDA itself doesn't actually scale your application. What KEDA does is it interacts with horizontal pod autoscaler to increase the number of instances of your application. So you're still adding and increasing a number of replicas, or decreasing perhaps a number of replicas. So KEDA itself isn't actually scaling. What we're doing is we're using some of those native scaling systems that already exist on Kubernetes to scale our application. When you make a deployment to your Kubernetes cluster, you will also define what's called a scaled object. And this defines the configuration that your application should scale under. And we'll drill into that a little bit now. So let's imagine that we want to scale our application based on messages in a queue, perhaps. So we will define a configuration for our given application. And that will use an SQS scaler. And this is the configuration that we would use. So first of all, we would define our scale target. So this is the deployment that we need to be scaling once we hit our particular parameters. We then have a polling interval, so how often we want to poll our queue to see if there's any messages in it. We then have a replica count when idle. So sometimes when we've got no work for our system to do, we want it to scale right down. So that's how we control it here, because it's not just about scaling out, it's also about scaling in as well. And we then have, I don't know if everybody can see it, right at the bottom of the screen, the source. So this actually says which queue you need to go and look at. So, and you define this with a URL and a name of your particular queue. So with this configuration, we can say, hey, for our particular deployment, our credit card transaction, settlement system, processing system, whatever it's called, we want you to be looking at a particular queue. And that queue could be Taylor Swift payment requests queue for all intents and purposes. The great thing with KEDA is it doesn't just have to react to what's going on live with your particular event integration technology. You can also have scheduled scaling with KEDA as well, where you will scale at a particular time and interval. So perhaps if you are that merchant bank or that acquiring bank, and you want to scale your payment and settlement systems the day before or a few hours before pre-sale starts, this sort of configuration would allow you to do that. So you can define the date and time when you want to scale that application. So those known events or that planned event that you've got, you can also account for those as well. You're not just offloading everything to your event-driven scaling. So this allows you to scale your workloads based on some event. And we know that there are events flying across our journey when we are making a credit card transaction. But this doesn't actually help us if we don't have sufficient compute in our cluster to actually run these workloads. So if we don't have sufficient compute available through our worker nodes, our data plane, it doesn't matter that we've got this great system in place. What we're going to end up with is a load of instances of our application that don't actually run. So that's when we need a data plane scaler. Now, there are two options there, Cluster Autoscaler, and Karpenter. And what I want to speak to you about now is Karpenter. So Karpenter was originally built by AWS. It's about 18 months, 2 years ago now. But it's been contributed to the CNCF as a project there. So it's open source, and it's what we consider to be application-centric scaling. So it adds compute to your cluster based on what your applications need. So it's going to look at what your settlement systems, your credit card payment systems, it's going to look at what they need and scale and add compute to your cluster based on that. So the way Cluster Autoscaler works, just to contrast the two. So Cluster Autoscaler will kick in when you have what we consider to be unschedulable pods. So let's imagine we have either a KEDA event or there's some sort of resource threshold that's been breached, and horizontal pod autoscaler has kicked in and said, okay, we need to increase the number of replicas. The Kubernetes scheduler will attempt to schedule those replicas, but if there's no compute available or insufficient compute, they will just be marked as unschedulable pods. At that point with Cluster Autoscaler will kick in, and it will add compute to the cluster. Now, it does that, in Amazon EKS, it does that by interacting with what we can call node groups. And node groups are, I suppose, logical collections of like or similar compute. In AWS terms, what we're really saying here is the same EC2 instance type. And you will define node groups for your cluster. So you might have node group 1, which uses a particular EC2 instance family. You might have node group 2, which uses perhaps Amazon EC2 spot instances if you want some cost optimization in your cluster. But you will have lots of different node group configurations. And Cluster Autoscaler will pick which one of those node group configurations that it wants to increase, and that will add compute into your cluster. This is really great when you've only got one node group configuration. When you've got lots, that can be a bit of a challenge because you need to give Cluster Autoscaler some clues as to which ones to pick. Equally, the more node group configurations you have, that's going to be more of an overhead for your teams that are looking after your Kubernetes clusters. They're going to have to be aware of all of those node groups when it comes to things like upgrades and patching. Equally, it means that your teams who are looking after your cluster need to be aware of the types of application deployed to your cluster to make sure that there's the correct type of compute available. Say if your teams suddenly want to deploy a Gen AI workload to their Kubernetes cluster, and they now need access to GPUs, for example. You as a Kubernetes administrator will then need to create a node group configuration which adds GPUs to your cluster. So this is how Cluster Autoscaler works. And where you have a small number of node groups, or where you've got lots of similar applications that run on the same type of compute, this is great. But where you get lots of different types of applications, lots of different compute needs, actually this can result sometimes in an increased overhead for your platform teams. So Karpenter works a little bit differently to this. So Karpenter still responds to the same events that Cluster Autoscaler does. So we still have these pods that need to be scheduled and need to run somewhere. So KEDA, HPA have kicked in, they've done their thing. They say, we need more of this credit card processing system, whether it's settlement, clearing, whatever. We need more of these. And we've now got these pods that need to be scheduled somewhere. Kubernetes schedulers tried to schedule them, and we haven't got the right compute. So at that point, Karpenter kicks in. And what Karpenter does is it communicates with our AWS EC2 Fleet API. Now, when Cluster Autoscaler kicks in and tries to add compute into your cluster, this is an asynchronous call. So it will wait a period of time. When it gets a response back, we can act on that, and that EC2 compute is added to your cluster. With Karpenter, the Fleet API is a synchronous call, so it kind of gets an instant response back. So there is a bit of a time benefit there to using this as a way to add compute. And what Karpenter actually does is it looks at what your pods need. So it looks at all the CPU and memory that your pods need to run, and then it calculates the right size of EC2 instance that should be added to your cluster in order to run those pods. So it's not using a predefined configuration that tells you, use this EC2 instance with this much CPU and memory. It makes that decision. And by offloading that decision-making to Karpenter, it means that you don't need to have all these predefined node configurations. It means that as AWS is updating its EC2 instance types and families, you can benefit from all of those because the logic exists within Karpenter because it's communicating with our AWS APIs. And what Karpenter does is it picks the right type of compute to add into the cluster based on what the pods need. And it does this in two different ways, dependent on which cost strategy you want to use. So if you want to use on-demand compute, Karpenter will pick the cheapest type of EC2 instance that is big enough to run your pending pods. If you want to use Amazon EC2 spot instances, it uses a slightly different, what we call capacity optimized strategy, where it looks at the capacity pool with the most spot instances available that's also the cheapest. So from a cost optimization perspective, Karpenter is also really cool as well. So not only is it communicating with that Fleet API, which has performance gains over communicating with the standard EC2 API, it's also making a cost decision when you're adding in compute to your cluster. Because if you suddenly want to scale to handle these millions and millions of Taylor Swift fans, that's also going to have an impact on your bottom line in terms of the cost of running your compute infrastructure. But you do still want to give Karpenter a bit of a steer as to what type of compute to pick. You want it to pick the right compute to run the pods and the cheapest compute, but sometimes there might be additional configurations that you also want to say. Maybe there's particular EC2 instance families you want to avoid. Maybe you've done particular performance testing on some particular spec of compute, and you know that that is optimized for your workload, so you only want Karpenter to pick that sort of compute. And you can do that using node configurations that you can pass to Karpenter. And for these node configurations, there are some different strategies that you can use, what we call single, multiple, and weighted. And what these do is they give Karpenter a bit more of a steer so that it knows what type of compute to actually be picking. So it's not just going to always pick the cheapest compute of all the EC2 instance families available. It has some steer to say, actually, avoid these EC2 instances, or maybe favor these EC2 instances because maybe we have some commercial product in place, like an EC2 instance savings plans, and we get discount on these ones. So these are the ones we want to focus on and we want to pick. So that you can control what Karpenter's picking, but really you're offloading that decision making to Karpenter. So if we think about our Taylor Swift problem again, we now have KEDA that's going to scale based on the number of messages in a queue. Perhaps those messages are, I want to buy this ticket now. And we now have Karpenter that's able to pick an EC2 instance that's got enough resource to run all of those replicas that we now want to schedule. And it's going to pick the cheapest EC2 instance, which is really cool. So from a configuration perspective, it looks a little bit like this, where you can be really specific in terms of the type of compute that you want to be added into your cluster, or perhaps not added into your cluster. So Karpenter actually lets you control that. And Karpenter also keeps count of the amount of CPU in your cluster as a total figure. It wants to make sure that your cluster has enough resource to run your applications. It doesn't mind if this resource is split across one node or 100 nodes, but it also wants to make sure that you keep within the amount of CPU that you need, and that can be controlled with a CPU limits configuration. Karpenter allows you to control the type of architecture that you're using, so whether you're using AMD, Intel, Graviton, ARM, you can use all of these different architecture types. Equally, you can use different purchase options with Karpenter using the capacity type configuration, so you can select if you want to use spot or on demand or both in your cluster. Now, Karpenter is open source. It's available for you to install today on your clusters, so you can have a play and you can really see from a performance perspective and scaling perspective how it differs from cluster autoscaler by running some of those performance tests. One of our AWS heroes about a year ago did run some performance tests using cluster autoscaler and using Karpenter to scale up to 10,000 pods as quickly as possible, and did see some performance gains with using Karpenter over cluster autoscaler. So I'd encourage you to go and look at that blog and go and test this out for yourself. There are definitely performance gains to be had there. If you want to test out Karpenter and KEDA together, we do have a GitHub repo available with some example code which will provision a cluster for you, install Karpenter on it, install KEDA on it, and an example app so that you can really step through this and see how it works. So that's a little bit about Karpenter and KEDA, but does this actually solve our Taylor Swift problem? So bringing it all back to Taylor Swift. So we still have our millions of fans that want to purchase these tickets. You know, they fought the battle of getting access to pre-sale. They fought the battle of getting access to the ticket retailers so that they can add their tickets to their basket, and now they want to make that payment. So we have our Taylor Swift fans who wants their tickets so that they can change their lives forever. And they want to make that credit card transaction to do that. So that's that really nice flow diagram we saw at the beginning with the different events passing through. And what we really want to happen is that the Taylor Swift fan invokes that credit card transactions, and then the systems that support that credit card transaction, so those merchant bank systems, those settlement and payment clearing systems, actually scale up based on the user demands. So they're not scaling anymore based on some CPU memory threshold or utilization. They're scaling based on the number of events that they need to process. And that can be achieved now using KEDA. So what could this look like in practice? So we've got our Taylor Swift fans who are making a number of credit card transactions, and that is generating an event which is popped on a queue. That queue is being polled by KEDA. So that queue could be Taylor Swift fans wanting to purchase tickets, queue name, whatever you want to call it. So KEDA recognizes that there's messages now in the queue and that we need to scale. So KEDA will interact with horizontal pod autoscaler, and that results in pending pods. So these are our payment systems, our settlement clearing systems. These need to scale. And we now have those pending. Our Kubernetes scheduler needs to schedule these. So in the first instance, the scheduler is going to try and schedule these on the existing capacity that we have. But where that capacity doesn't exist, Karpenter will now kick in and add the compute that we need in order to schedule these pods. So that compute is added in, and Karpenter can now schedule these pods on the system. So now we have more replicas or more instances of our payment applications to handle and process all of these messages in our queue, which ultimately results in messages being passed to our merchant bank or our acquiring bank to help us make these transactions and help our fans actually buy their tickets. So some takeaways then, and don't worry, none of the takeaways are actually about Taylor Swift. So KEDA in conjunction with Karpenter helps you optimize the resources in your cluster. It's no longer just about the compute utilization of your cluster. It's really about how do I get the right compute in my cluster, and how do I get the right number of replicas and instances of my application to support the load that I actually need to run. Using Karpenter and KEDA together, you now have much more of a dynamic scaling system in place. You're scaling based on the events that are happening in the outside world. You're not scaling based on your infrastructure. You're scaling based on the needs of your Taylor Swift fans. By utilizing KEDA with Karpenter, you can actually enhance the performance of your applications because you're providing the right compute that your applications need. You're not adding in compute to your cluster based on this predefined single node configuration. You're letting Karpenter pick the compute, which means that there's a much more diverse pool that can be added into your cluster. Karpenter will also allow you to simplify the management of the compute in your cluster. When I was mentioning node pools, you will have a configuration based on each one of your node configurations for cluster autoscaler. With Karpenter, you can have a single node pool configuration or a single Karpenter configuration if you like, and that reduces the overhead on your operations teams when they're thinking about things like upgrades and stuff like that. And you can actually start to shift your entire mental model and your approach for scaling. So you're now not scaling on CPU and memory, you're now scaling on the metrics that actually matter in your system, whether that be queue depth, whether that be a message that exists in something like Kinesis. So you can now start scaling your applications based on the number of Taylor Swift fans that are trying to buy a ticket, or maybe not the number of Taylor Swift fans, maybe the number of Glastonbury fans that want to buy a ticket, maybe the number of opera fans that want a ticket to the Neville Hall opening of the summer season, and this is the one event that they really want to go to. But this is all about how do we move away from this idea of 80% utilization is when we want to scale, because at 80%, we might already have unhappy Taylor Swift fans. And as we've seen on social media and Twitter, nobody wants an upset Taylor Swift fan. So thank you very much.